Just a quick mic check. Can everyone hear me?
Yes, Professor.
Okay, awesome. Okay, welcome everyone. So we're going to get started with chapter 19. Anyone have any questions before we begin? All right, so let's get started then. So chapter 19 focuses on the ionic equilibrium. So we're still dealing with equilibrium. In particular, we are going to focus on acid-base buffers. Okay. So for acid-base buffers, the number one thing you need to know about this is that an acid buffer is made up of two things: the weak acid plus its conjugate base, or a weak base plus its conjugate acid. Okay. That's mainly all you need to copy down from the slide here. Does anyone else need time before I move forward? Okay. So when we are talking about the effect of buffers, if I look at a scenario where I do not have a buffer, if I have a pH of 5, if I add in just even 1 milliliter of a concentrated acid, it becomes a pH of 2. Or if I add in 1 milliliter of NaOH, it immediately becomes a pH of 12. So it changes the pH significantly just by a small amount. Now, if I had a buffer, you'll notice that the change is very, very insignificant. The pH changes by 0.02 instead. There's a very big difference. Anyone have any questions so far? Okay. So how buffers essentially work is it uses a thing called the common ion effect. So if I look at the example I have on the screen here, this is my acetic acid. I'm looking at just this H right here, okay? If I take away the H, it becomes my conjugate base. So once again, if I take away this H, it becomes my conjugate base, and then I have some kind of acid here, all right? And how this essentially works is if I add in acid, when I'm adding in an acid here, it should be H+. What is going to interact with the H+? Is it going to be the acetate or is it going to be the acetic acid? This is the part where you answer the question. Just a quick check. Can everyone hear me? Okay. So if I added in some kind of acid here, I have here a conjugate base, right? And I have here a weak acid. If I'm adding in some form of acid, H+, for example, what is it going to interact with? The base or the acid? It's going to go ahead and interact with the base, okay? When I go ahead and add an H here, what does it become? It just simply becomes the weak acid, okay? So I add in some H, it changes my acetate into my weak acid or my acetic acid. Now, if I added in some base instead, OH, what does that interact with? What is my base going to interact with? It's going to interact with my weak acid. So it's going to go ahead and join with this H, and it's going to make more water, okay? And we go ahead and put that to the side. Once I take away the H, what is left? What do I end up making? If I take away this H, what is that? The ion, also known as my conjugate base, right? So I take this away, I'm making that. If I add in some acid, I'm making that. So it's switching between the two of these, essentially. So I'm not changing the concentration that's there. I'm just increasing it very, very slightly. But I am not allowing any random H's or any random OH's to enter into my solution so that it does not affect my overall pH. So just as the example I gave you here, if I added in, well, actually, I'll give you that example in the next page, okay? But this is the common ion between the two of these, between the weak acid and the conjugate base. Okay. Now let's talk about how a buffer works. Okay. So let's actually talk about how a buffer works. So if I look here, once again, I said, if I add in my OH, it will interact with the acid to make water, and then I will form my conjugate base. If I add in some amount of acid here, it will interact with this conjugate base and form my weak acid. Any questions up to this part? Okay. Does anybody need time to copy this before I move forward? All right. I see a hand raised, so I'll wait a little bit.
I have a question actually.
Yeah, go ahead.
So when reacted with the OH, does the what does the molecule become?
So if I'm looking at the example on the screen right here, right? This H is going to react with this H. The two of these are going to make water. Okay? That makes sense?
So there would be an extra water formed on the left side of the reaction?
Yeah, but we don't care about the water, right? Because if you think about it, water is liquid, so I don't really care how much water I make. Okay? What I do care is about this CH3COOH minus, which is essentially just that. So I'm increasing the concentration of this. I'm decreasing the concentration of this. That make sense?
Yeah, I see. Thank you.
Okay. All right. So looking at how a buffer works, once again, if this is my buffer, I have an even amount of these two. I add in some acid. And what happens is it will interact with my conjugate base, using up some of it. So this goes down, and then the other one increases. Remember, these are all very slightly changed. So as long as you have some amount of your buffer that can resist the change, you are good to go. The pH stays almost the same. This little change right here changes the pH by a very small number. So we're talking about like 0.02 difference or 0.01 difference. If it did not have these buffers, and it was just in water, it would just be purely that H plus or purely the OH minus. No, the buffer is this. The buffer is made up of two things. Once again, the buffer is made up of two things. It's made up of your weak acid plus conjugate base, or your weak base plus its conjugate acid. Okay, does anyone else still need more time with this? All right. So let's talk about the relative concentration of buffer components. So we know that our Ka is a way to determine the acid strength, okay? We can also use Ka to kind of determine the ratio of our buffer. So this is my weak acid, right? And this is my conjugate base. If I look at the ratio of this, if I increase the ratio, that means I'm getting more of these and less of these. The overall pH should increase. If I have the opposite scenario where I have less of my weak acid, more of my conjugate base, my overall pH.
Professor Ho,
Yes.
I'd like to interrupt in just a few seconds.
Sure.
To the whole class, I sent a link to you by email. And I think since you, Dr. Ho, you Professor, you just started, right? Okay, so how far you gotten? About 5 minutes?
Yeah, about 5 minutes in.
Okay, can you hold off just at this point? Let I need the class to follow that link on the email I sent and do the quick questionnaire. It takes about 5 minutes. That's all it takes. And so, you know, and then you can continue. And my apologies.
That's fine.
I had a little trouble logging in. That was my fault. So, you know, that, class, if you can get that done the next few minutes, then we'll resume. Okay, that's that the department wants you to do this, by the way. So thank you very much.
Okay,
There's
go ahead and work on.
There's one person. Let me get the name. Professor Ho. Let me get the name.
I think I know who you're referring to.
Vinod.
Yeah, Sneha.
Okay.
Vinod, right?
Yes, cannot reach her.
So your email is incorrect on CUNY first. So that's why we can't reach you by email. She's here though, so you can talk to her.
Okay, well, tell her to send me her correct email. And it's right now, I'm at edward.look at CUNY, at qc.cuny.edu, okay?
Okay, I'll send that to her right now.
Okay, no, thank you.
Thank you, Professor.
I'll just type it in the chat here so you can see it.
All right.
All right.
Okay.
So go ahead and take some time, fill out the email that Dr. Look sent you.
I'll be back in a sec.
Okay. So once again, fill out the email that he sent you. If you don't see an email, send him an email and ask him about it. I sent the email link. I sent his email link right there in the chat. Okay. So give me about 5 minutes to fill it out. 4:55. I'll still be here if you have any questions, but use this time to fill that out.
Professor, did you put the email in the chat?
Yes, I did.
I did
I'll
not
type it
see
again.
Okay, thank you.
Do you see that? Oh, sorry, I
Um,
sent it to the waiting room. I apologize.
Okay.
There we go. Everyone get that?
Thank you. Yeah.
Okay.
Thank you.
All right, to the people who told me you didn't get it, I will send it to you again. I'm sending it to the email address that I see that you sent me. Okay, so here it is. I will send it in a sec.
Professor,
Yes. Question?
Professor, did you check the quiz?
We can talk about it at the end. Okay.
Okay, thank you.
All right. Okay, just a quick check. Did everyone fill out the survey evaluation from the email? Anyone still working on it?
Should be
Okay.
done. It's a quickie, it's just basically, is he a
Um,
mean fella? Does he smell bad? Is he ugly? It's easy.
Yeah, basic stuff. So go ahead and fill it out. Try to be as quick as possible. You don't have to tell me if you finish. I'm assuming he gets the record of that. So just finish it and then we'll get started. Give you another minute with it and then we'll get started. Are you asking me or Dr. Look for that question, chat? I only teach Chem 114. And you just call me by my first name, it's not doctor. Okay, so does anyone else still need to fill out the survey evaluation? All right, let's continue then. So once again, looking over here, I have here the ratios of my weak acid and conjugate base. Okay, as long as this is increasing overall, then my pH should go up. Remember, when pH should go down. The concentration should go up and my pH should go down. Okay, and then the opposite is true here. When the ratio of my weak acid to conjugate base decreases, the concentration goes down and my pH goes up. All right, any questions before we continue? All right. So I want you to go ahead and try out this calculation. This question should look very familiar to you because we have done the exact question with 1 molar HF. Now we're doing 1 molar HF plus 1 molar NaF. A minus refers to the conjugate base. That's correct. So I'll give you a few seconds to start setting this up and then we'll go through it together. Okay. Okay. Does anyone else still need more time to set this up? Okay, so let's treat this the same way we would normally for a weak acid equilibrium problem. I have your HF plus H2O, and that becomes F minus plus H3O plus, okay? So what I care about is going to be how much H3O plus I have at the end. I know at the beginning, I don't care about the water. We can go ahead and ignore that category. So in the very beginning, do I have any H3O plus? No, right? So I'm gonna put a 0 there. What's my concentration for HF? 1 molar, okay? Now what's my concentration for F minus? So normally, if we're looking at just a weak acid equilibrium, then this would be 0. But remember, I mentioned that we have NaF now. Now for the Na, this is not going to interact with any of our stuff because this is the cation of a strong acid. So this will not interact with anything at all. But I do have F minus. This is the conjugate base, also known as the anion of a weak acid. Okay, so this does contribute to it, and this has a concentration of 1. So we start off with 1 here and 0 here. And normally we minus X here and we plus X on this side. Okay. Treat it the same way. 1 minus X. This is 1 plus X. And then this is now X. Any questions up to this step here? Okay, is it okay if I clear the screen? Then any time to copy it down.
Professor, sorry, just quick question. So we don't include H2O because I'm sorry,
Liquid.
I'm having a little bit of trouble with it basically. Just
So we don't
H2O.
include H2O because it is a liquid. So remember what we do in the equilibrium expression. What do we not include?
Oh yeah. Oh, okay. I see. Okay, yeah, now I see. Okay.
Okay, so remember, we
Sorry.
don't include solids and liquids. We only include aqueous and gases in our equilibrium expression.
Yeah.
So now that we get to here, 1 minus x, 1 plus x, and x, is it okay if I clear the screen?
Yes.
Okay. So let's plug this in. I have my Ka. I'm not going to write the number in because we know what it is. I'm going to set up my product over reactants. This is 1 plus x, and this is x over 1 minus x. Okay. Now, what can we always assume in any kind of weak acid equilibria? Or in most cases? X does not equal the initial. We can assume the 5% rule, right? So that the change is negligible. So if the change is negligible, what can I cross out? I can cross out the minus x in my denominator, but I can also cross out the plus x in my numerator. Okay, so I can cross out both of these. Now, with that said, this is just 1 over 1. I can just simply divide that. Ka is equal to my x, which is equal to my concentration of H3O plus, which in this case is just equal to 7.2 times 10 to the negative 4. Any questions? Now, when we get to here, are we finished? What else do we need to find? The pH, which is our negative log. So I just simply do the negative log of my Ka. Now, if I'm looking for the negative log of my Ka, what's another way of writing that? If I look for the negative log of H, I get pH. If I look for the negative log of Ka, I get what? Not Kb. So once again, if I have H plus and I'm taking the negative log of this number, right? It should give me pH. So it is pKa. Okay. The negative log of Ka is equal to your pKa. Negative log of OH is equal to your POH. Negative log of H plus is equal to your pH. Okay, so what did you get as an answer in terms of my pH? What was your number? If we look at it, it says 10 to the negative 4. It's anywhere between, I would say, 3 and 5 in terms of our pH. So 3.14, okay. So that is our pH. Does anyone need more time to write that down before we move forward? Okay. So let's give this a try on another equation. I want you to try this one out on your own, okay? Yes, to answer your question, in that scenario, pKa is equal to pH, only because that scenario worked out. And we'll explain more about that in a bit. So I want you to give this a try first. I want you to go ahead using the information up here. I want you to find just the normal pH value of this buffer solution, okay? The value of Ka does not change in general. This is a constant. So even if the concentration was 2 molar, 5 molar, whatever it might be, the Ka is a constant that does not change. But what will change is the value of X. So the change essentially, or how much it dissociates. X was not 1. X was actually equal to Ka. Does that answer your question? We got X was equal to your KA, 1/1 just canceled it out. So it was essentially 1 times X over 1 equals KA. So that's why we canceled out the ones. So in the scenario that we have here, you'll come to realize that 0.5 and 0.5 will cancel out so that your X is going to be equal to your KA again. Okay. All right, so I'll give you a little bit of time, set up your equation for the first one, and then we will talk about the next two. Okay, does anyone else still need more time to set up for our pH? Okay, so let's go through this real quick. Okay, so same setup, 0.5. We have 0.5 here because this comes from our salt. Okay, so CH3CO and A. And then we don't have our water, we don't care about that. And then we don't have any H3O plus to start with. So setup is the same way. Any minus X or plus X we remove, we simply assume that the percentage is small enough, less than 5%, that is negligible. Plug everything in. Same setup here. This is essentially equal to my X, which is equal to my H3O plus. Then I go ahead and take the negative log of this value, and I get my answer. The equation is already balanced, but yes, you should balance your equation every time you look at it. Good news for this is because we're dealing with a weak acid and its conjugate base, just a 1-to-1 ratio. Usually it mentions 1 molar, or it happens to mention 0.5 molar of each. Okay, does that answer your question? Okay. So once again, down here, we can also justify our percentage. It makes sense. It is less than 5%, so we're good to go. This is your pH value. Okay, I want you to write this down. If you have to write it on a piece of paper, go ahead and do so. We're going to look at the scenario if I go ahead and add either an acid or a base to this and see how much it actually changes by. Does anyone else need time to copy this down before I move forward? All right. So in our first scenario, we are adding in some amount of base. Okay. In this scenario, it's telling me that it's going to be 0.02 moles. So it's going to come out to 0.02 molar. Right? We add this, we set it up in our stoichiometry equation, very similar to our ice table as well. This is the initial amount that you had for each. Okay. Then I'm adding in some amount of base. Remember, the base is going to interact with my acid. It's going to join with this H here. The two of these are going to join together, and we're going to go ahead and make water. And what's going to be left over is, and once I take this away, I have some of this left over. Is anyone confused about this concept? Yes. So this is not the ice table change. This is just the stoichiometry change, but it's almost the same thing. Because you know how much you are adding in, and you assume that all of this is essentially a strong base, all of this will react with the acid. Does that clear it up for you? Okay. So once we get to this, this is my new concentration, these two values here, okay? So I'm gonna go ahead and set up my same acid dissociation equation. This time, instead of 0.5 and 0.5, I'm using 0.48 and 0.52. Okay, this is after I have already added in some of my base and has interacted with my buffer. Any questions on how we set up the ice table on the bottom here? All right. So with that said, let's put this into our Ka equation. So we set it up the same exact way. This time, remember, the minus x is negligible, the plus x is negligible. But now we no longer have the 0.5 over 0.5. This is now going to be your 0.48 and 0.52. So when we set this up, is that 0.48 over 0.52? That actually requires you to do some calculations. We can't just cross this out into 1. It doesn't work that way. Okay. So when you multiply this across, it is no longer x equal to Ka. It changes slightly. So the number comes out to about 1.7 times 10 to the negative 5, which comes out to about 4.77. And that is actually a 0.03 pH difference. So in this scenario, I've increased my pH by a very small amount, but it has increased because I've added in some base. So remember, the purpose of a buffer isn't to say there is no change in the pH. It just simply resists the change in pH. It reduces how effective the acid and base is at changing the pH. So this changes very slightly. Any questions about this before we move over to the next one? Go back to us for a second. Okay. This one right here. Okay. And yes, our acetic acid is going to be our product. Well, technically, it's going to be our reactant because that acid is interacting with the OH and we are making CH3COO. So we're making the conjugate base as our product if we're looking at products and reactants. Does that answer your question? Okay, so let's go back a step. First, I have some amount of my weak acid, some amount of my weak base, conjugate base. Does that make sense so far? Okay, I am now adding in OH. This is a base, right? This base is going to interact with this acid. Now, I don't have a lot of this base. I only have this much, 0.02. So I'm not saying I have 0.5 molars worth. I have a smaller amount. That entire base is going to completely react with this acid here, okay? It's going to take away some of that H. These two are going to join together and they're going to make water. Does that make sense? Now, I took away some of this acid, so that's why we are subtracting from this number. That's why this is the new concentration of that acid. Does that make sense? All right. With that said, if I take away the H here, what is this? You're not sure? What does this look like? The base. So it is the conjugate base. Remember, conjugate base is whatever the acid was minus the H, okay? So I've essentially made the conjugate base by taking away an H from the acid. Does that make sense? Okay, so that's why I'm adding it to this side because I'm essentially making the same stuff that I already have. That is why this concentration increases and this concentration decreases. Does that clarify everything for you? Okay. Is anyone else confused about this concept? I want to make sure you understand it. This goes back to stoichiometry. Because if you don't understand this, you're going to have a hard time with the rest of what we're talking about today. Okay. So with that said, we already determined that this was 4.77. Let's look at another scenario. Going back to my original buffer, if I decided to add in acid instead. So I set up the same way. This time, if I look at my equation here, my conjugate base is going to interact with the acid. The two of these are going to join together. I'm going to take this H, I'm going to throw it over to here. This is going to make my weak acid. Does this make sense to everyone so far? I'm taking the conjugate base, I'm adding an H to it. So it is essentially becoming my weak acid. And in the process, I am using up some of my conjugate base. So concentration wise, I should have less of my conjugate base, more of my weak acid. I will assume your silence means you understand it. Okay, with that said, we plug in our new values here, do our ice table using the new numbers. And again, everything we're doing here is just simply flipped. Okay. If you notice, this is always going to be my weak acid plus my water forms my conjugate plus the acid separating, so H3O plus. Okay, any questions before we continue? All right. So with that said, we plug everything in. The minus X plus X, I can ignore it again. My pH comes out to 4.70. And if I look at the ratio here, this is actually going to be a little bit higher than the 1.8. That's where we got this number. And that is how we get the 4.70 pH. And in comparison to the original value, it is a little bit lower because I've added in some acid, so the pH should go down. If you add in acid and your pH goes up, something is wrong with your calculations. Okay. So this change is very, very insignificant, is 0.04. And in the previous one, it was 0.03. Does that make sense so far for everyone? Okay. Now I want you to go ahead and try this out. I am looking at 0.01 moles. So instead of 0.02 moles from our previous example, I have less concentration. In fact, half of the amount. Okay. And I'm adding it to water, not to a buffer. I want you to go ahead and tell me what the pH should be. So I'll give you a second, set up what you have to set up, and then I will show you what we're doing here. Okay, so really quickly, what is the pH of normal water? 7, right? I want to put that to the side, okay? I'm going to keep that to the side now. I have added in this amount into water. So 0.01 moles. I'm going to switch that into molarity. I'll do 1 liter. This is going to give me 0.01 molarity. Okay, is everyone on the same page so far?
Yep.
This is the concentration of OH minus, and I have nothing else that's going to interact with this buffer. I want you to calculate the pH given this information here. Find the pH of the solution based on what I have just added in. Give you a few seconds to do that. Okay. So someone already got an answer. It should be pH of 12. Anyone confused on how we got pH of 12?
Professor, can you just show the calculation real fast?
Sure. I have 0.01 molar OH minus, right?
Yeah.
I can do this in 2 ways. I can change this into POH, right? And then change
Yeah.
that into pH, or I can change this into H plus by doing KW divided by OH minus, okay? The easier one for me is just going to work with POH. I do the negative log of this value. This is the same as if I wrote 1 times 10 to the negative 2. Okay, so that'll give me a POH of 2. And with the POH of 2, once we get that, you know that it is 14 minus 2. Let me clear the screen.
Oh, okay. Yeah, that makes sense. Okay, thank you.
Okay. So any questions on that? We went from a pH of 7 all the way up to 12. And if you look at the amount we added 0.01 moles of it, right? In our previous scenario, when we dealt with the buffer, I added in 0.02 moles of it. So I added twice the amount of this. That's okay. I added twice the amount of my OH here, right? And my pH only changed from 4.74 to about 4.77. Okay. So this is the difference between having a buffer versus not having a buffer. Any questions before we continue? Okay. Now we can go ahead and look at this. Again, this is just breaking up the ratio, same format. We add in a strong acid, it will interact with the conjugate base, and then it will form more of my weak acid. So the ratio increases in my weak acid, it decreases in my conjugate base, and then we end up with here, lower pH in the process. And this one ends up with a higher pH. Any questions about this? Yep, it's a very marginal difference as long as you have a buffer that can resist the change. So if I went ahead and I just wrote this out, my weak acid and my conjugate base, the conjugate base is going to resist any addition of acids. The weak acid is going to resist any change when we add in base. And as long as you have one of these, it can resist that thing. So if I run out of weak acid, then I have an issue. If there's no more weak acid and I add in some OH, this is nothing to change the weak acid or the OH into conjugate base. It doesn't exist anymore. So then this just shows up in my solution and that sends my pH skyrocketing. Does that make sense? Okay. So there is an equation that you can use that is going to help you figure out the pH, just the pH of the buffer, okay? So this is known as the Henderson-Hasselbalch equation. If you look carefully here, this base, and I want you to make a note of this, refers to your conjugate base, okay? This acid refers to your weak acid. So I want you to make a note of that. We can also write down the other form of your Henderson-Hasselbalch equation. POH is equal to PKB plus the log of your acid over your base. Now with this written here, what can you tell me about this acid? And what can you tell me about this base? What kind of acid is it? What kind of base is it? This is the conjugate acid, right? And this is the weak base, okay? Remember, our buffers can be made up of two things, weak base plus its conjugate acid or weak acid plus its conjugate base. So this is the equation you would use when you're solving for a weak base conjugate acid equation. And this is your weak acid conjugate base equation. Now remember, these equations can only be used for buffers. If you just had a weak acid or just a weak base, it would not be used. Okay, any questions? All right. Does anyone else still need time to copy down this equation? Now, going back to a point that someone mentioned earlier, what happens if the concentration of my conjugate base and weak acid were equal to each other? We'll just say they're equal to 1 to make it easier for ourselves. If they were both equal to 1, what happens to my equation here? It equals pK. The reason why is because this becomes 1 and 1. So 1 over 1, log of 1 equals 0. Okay? So then I can say that if the concentrations of my weak acid and conjugate base are equal to each other, my pH is equal to my pKa. Same thing as if I was saying my H plus is equal to my Ka, which was equal to our X. So when we solved it earlier, we had 1 molar and 1 molar, or we had 0.5 molar and 0.5 molar. So they would essentially cancel each other out. My pH would be equal to my pKa. Any questions? And once again, if they ever give you a buffer scenario where the conjugate base and the weak acid were equal to each other, they make it very easy on you, and this becomes simply 0, and you get this information right here. Okay. Now, it's not always going to be the case. A lot of times they will have different concentrations, which you will then need to calculate your actual pH value. Okay. So anytime you hear that there is a buffer, you should use this equation. Now let's talk about the buffer capacity. So 2 things you want. The higher the concentration, the more effective the buffer. The more you have of this buffer, the more it can resist the change in pH. The other thing is, the closer that these 2 concentrations are to each other, the better they are at resisting the change in pH for whatever scenario. So just as I mentioned before, my weak acid, my conjugate base. If I added in some H plus, what is going to stop this H plus from changing? Well, what's going to stop this from changing my pH in my solution? Is it the conjugate base or the weak acid? I want you to think of this as a team. The weak acid plus conjugate base works together as a team. Okay? They each have their specialty. If I added in some acid, what is going to resist the change of my acid by using up that acid? The conjugate base. This is going to interact with this one right here. And again, it's going to make more weak acid. So it's not making something completely different. It's making stuff that it already has. Okay? If I added in some OH minus, what is going to stop my OH minus from changing my pH? The weak acid. So it's going to go like this, and then it's going to essentially make more of my conjugate base. Okay? So they both work together, but one targets the acid and one targets the base. So the weak acid will target the bases that approach it. The conjugate base will target any acids that join in. Okay? And so we want these 2 concentrations to be close together, because then you have enough to deal with both any acid that joins in or any base that is added in. So it can handle both scenarios. And we obviously want both concentrations to be very, very high. Any questions? Okay. So an example I can give you here. If the initial pH was 4.74, okay, and I added in some kind of strong base. If I have 1 molar concentrations of both my buffers of my weak acid plus conjugate base, if I add in some amount of strong base, it should change the pH only very slightly. But if I had less of that, so 0.3 molar instead, then it should affect my pH even greater. If I had such a small amount, 0.03 molar, it should affect my pH much more significant. But if you look at the numbers relative wise, 4.74 to about, I would say this is like 5.06 or 0.05, right? It is still a very small change, but it's relative based on the concentration. Now, if we have no buffer whatsoever, then we would be seeing a pH of 12 in the process. Does this make sense to everyone? Okay. I will take your silence as a yes. So let's talk about the buffer range. Remember we mentioned that the ratio of these 2, if they're close to 1, or if they're exactly 1, then we can say that my pH is equal to my pKa. If they are not exactly 1, right, and the ratio is a little bit different, so I have a little bit more of this and a little bit less of that, then we need to go ahead and add in whatever this value is, log of that information. Okay. So we can actually make buffers. And the way we go ahead and make a buffer is I find an acid where I want the pH number to be close to. Let's say I want the pH to be, making up a number here, 5, okay? I want to find some kind of weak acid with a pKa close to 5, usually plus or minus 1 pH worth. So something that maybe like 4.6 would work, or something that's within like 5.7, something close to 5. And then at that point, I adjust the amount of my weak acid and conjugate base. If I want it to be a higher pH, I add more conjugate base, less of my weak acid, okay? So that I can make this number go up or make this number go down to equal to 5. Give me 1 second. Okay, sorry about that. So once again, we want to make sure we find some kind of weak acid that's close to the number, and then we adjust the ratios of my weak acid and conjugate base to get to our pH value. Any questions before we continue? All right. So just as I mentioned, preparing a buffer, find a weak acid close to that pKa, use that to adjust your ratios of your, to get the desired pH, which means you're either making more of my weak acid or more of my conjugate base. And again, you don't want to pick something that's completely off. So let's say I want a pH value of 5. If I find some kind of acid that's a pKa value of 8, I am never going to reach this number, because you would need to add in a lot of your weak acid, and then that might throw this whole thing off. You want to make sure that the buffer is good at resisting both changes. Okay. Any questions before we continue? All right. So the next thing I want to talk about is acid-base indicators. How many of you have heard of a term called phenolphthalein? In your Chem 113 lab, right? Or sometimes in your Chem 114 lab. Okay. So phenolphthalein is an indicator. If it turns into a basic solution, so it becomes a pH greater than 7, usually around 8, it will start to turn pink. So it remains colorless if it is below 7.0 pH wise, and then it starts to turn pink when it is around 8.0. So it's what we can use to indicate that the pH has changed. Okay. There's actually quite a few of these. As an example, we can take a look right here. Again, you don't have to memorize any of these, but you get the general idea. They work in a range between 1 to 2 pH change. So like you can get things such as your phenolphthalein. If it is below a pH of 8, it's a clear solution. As it goes further up into the pH scale, it starts to turn into a pink and then dark pink. So this is our way of indicating whether or not we have hit that pH without actually measuring the pH value. Any questions before I continue? All right. So an example I can give you here is bromthiamyl blue. If I look at this pH range right here, it's about greenish, somewhere in the middle, when it's anywhere between pH of 6 to 7.5. As I get into a more basic solution, it starts to turn blue. And if I get to a more acidic solution, it starts to turn yellow. So if we're doing some kind of titration reaction, we can use this as an indicator to tell us that we are now entering the pH range of 7. We're in the pH range of 6 to 7.5 or less than 6. Okay. Anyone have any questions on indicators before we move forward? It depends on the indicator. Sometimes it will not change. So if you have an indicator that does not change at a certain range, like phenolphthalein, for example, if you were looking at the difference between pH of 6 and pH of 3, it will be colorless the whole time. It makes no difference. But if we're looking at the change between pH of like 6 and pH of 9, then you will see a difference. It will start to turn more pink as it gets more higher up past the range of 8. Does that answer your question? Okay. So This is going to be the heavier part of this topic. We are going to learn about acid-base titrations. So you need to use a lot of the knowledge you had from before in terms of molarity, in terms of ice tables, equilibrium, and acid-base equilibrium in general, okay? So you need to put all those together here. This is going to be a very math-heavy part. So be ready for this. Now, with that said, a couple of terms you should be familiar with: equivalence point and end point. So equivalence point means that the concentration, in other words, the moles of my OH is equal to the moles of my H3O plus. Okay, that means the two concentrations of my acid and base are equal to each other in terms of moles. All right, and our endpoint usually means an indicator change. So something where we're trying to find. We have different indicators for different points. Sometimes an indicator could be in the middle of an acidic solution, could be in a basic solution, could be neutral, could be any of those combinations depending on what you are looking for. Okay, let's continue. So I'm going to give you a couple of examples here. If we look carefully here, this happens to be exactly at 7, right? This is an equivalence point because we're looking at strong acids, strong bases. What do I know about strong acids and strong bases? What do they tend to do?
Dissociate.
Fully dissociate, okay? So I'm going to get a bunch of H and I'm going to get a bunch of OH out of that, right? This is going to come from my acid. This is going to come from my base. If I hit the equivalence point, what's happening is this concentration equals this concentration, right? So the amount of H plus and the amount of OH minus equal each other. So what I have here in the solution is a pH of 7 because these essentially make water. What is the pH of water? Assuming 20 degrees Celsius.
Isn't it 7?
It is 7, right? So that is why the equivalence point is 7 because these two added together make water. Anything left over from these, a strong acid and a strong base, this goes back to our talk about salts. Let's say we look at NaCl, right? That comes from, the Na comes from the NaOH, the Cl comes from the HCl. The two of those will not interact with water. Well, I mean, they will interact with water in terms of intermolecular forces, but not in terms of our pH. So they're not going to take away a hydrogen or add a hydrogen to it. So in terms of that sense, they do not interact with our pH value. So water remains happily at 7.0. Any questions? Okay. So let's break down this in terms of calculations because we will need to do calculations for this part for your strong acid, strong base titration. This is going to be our easier calculation. Then we're going to do a more difficult one. Okay. So we're going to break this up into 4 categories. I'm going to call it my A, my B, my C, and my D. Okay. A is my initial. So this is what my pH is with just my acid. So this is under the assumption that I'm adding the base to my acid, okay? This has just acid. My B is before equivalence point, okay? So I'm just writing it as before EQ. And this is at equivalence point, and then this is after equivalence point. So I want you to imagine this in terms of a beaker. So what do I have in that beaker? In my initial right here, I have just my acid. So some amount of acid, okay? In my B here, I have some amount of acid and I've added a small amount of B. Not enough to overtake the amount of A, but some amount of B, okay? And this can vary because I can add a little bit or I can add a lot as long as it is before the equivalence point. When I hit the equivalence point, that means the amount of my acid should equal the amount of my base. They should be directly equal to each other, okay? And then the last scenario, after equivalence point, I should have more B than I do A. Now, question for everyone here. Am I adding any acid across this whole thing? Outside of the initial amount of acid that I have? Have I added any acid? No, right? The only thing I am adding here is going to be base. So this A, this number, whatever it might be, right, remains the exact same throughout the whole thing. Okay, the initial amount. I do not change how much I'm adding. The amount of base is what I'm changing. So this is a little bit, this is equal to the amount of acid, and this is more than the amount of acid. So in terms of our pH, this should be a very low pH. This should still be a low pH, but it should start to rise a little bit. this pH, because we were given this, should equal 7, and this pH should be greater than 7. Any questions on that so far? Now, this is the concept-wise. We're going to go ahead and look at the calculation-wise to figure out the exact number. Does anyone need time to copy this before I move forward? All right, I'll leave it up for a little while longer. Now remember, this applies for all scenarios. Doesn't matter for what combination, strong acid, strong base, weak base. It will always apply. The amount that's in there, the pH values may change. So we don't have to worry about that right now, okay? But these what's inside of the beaker is very similar as well. Okay. With that said, your initial pH is your A here. Your pH before equivalence point is going to be your B. So we're going to learn how to set up these equations and do this calculation in a bit. For now, if you need to copy any of this down, go ahead and do so. This is going to be the main focus of chapter 19. It's going to be titrations. We have buffers, we have titrations. Then we're going to talk a little bit about the slightly soluble compounds. And that is mainly it, those three main parts. Obviously with a lot of math included. Okay. Does anyone else still need more time to copy down the equations here? Or copy down the information? All right. About a minute to copy it down. Okay. So the next two equations you're gonna next two types of equations you're gonna copy down is your pH at equivalence point. Good thing about this is if we're assuming strong acid, strong base, it is automatically equal to 7. You don't need to do any calculations. If you did the calculations, you would have ended up with the same value, 7. And the last one is pH after equivalence point, or in this case, they say beyond equivalence point. So I'll give you a little bit of time to copy this down, and then we will do one example with it. Okay, so let's go ahead and try out a calculation with this. I'm assuming everyone has copied this stuff down. Let's jump right into it. Okay, so this is the information you were given. 40 milliliters of a 0.1 molar HCl, and we are titrating it with 0.1 molar NaOH. We're lucky because in this scenario, the two concentrations are equal to each other. Okay, so what I can say is that I know that if I had 40 milliliters of this, then the two of these are at equivalence point. Okay. In our very first scenario, when I'm looking at A, we are looking only at the amount. That's very funny. So really quickly, if we're looking at the amount of our base here, we have our A, we should have 0 milliliters to start. Okay. For B here, I should have some amount that it's greater than 1, but less than 40. So something like 1 to 39 milliliters. Because I know that C, my equivalence point, should be 40 milliliters. And last, D here is anywhere greater than 40 milliliters. Does this make sense so far? Just concept-wise.
So could you just explain part B?
Part B, sure. This is always going to be in my beaker, right? 40 milliliters of this concentration of acid. Can we agree on that?
Yes.
Okay. And the very beginning, did I add any base?
No.
No, right? So that's why 0 milliliters, I can do this calculation right here. I solve for that, okay?
Mhm.
The second I drop a little bit of base, so we'll just say 1 milliliter just for continuation-wise, a solid number, because you can even say 0.001 milliliters of a base, okay? But 1 milliliter of a base, then this is now into my before equivalence point category, because now I have some acid plus some amount of base. Does that make sense?
Yes, thank you.
Now, the amount of base that I add can vary. I can add a little bit more base, a little bit more base, as long as it is less than the amount of acid. Because when I come to the equivalence point, the amount of acid is equal to the amount of my base. As long as this B is a little bit smaller than my A, it is considered before equivalence point. Does that make sense so far?
Yes.
Okay. Now, with that said, this is the fun part, okay? This initial concentration, there's only one calculation you can need to solve for it, and you're done. This equivalence point, there's only one calculation you need to solve for it, and you are done. Before equivalence point, I can have many calculations here. I can solve for it with 1 milliliter of NaOH, 2 milliliters, 3 milliliters, all the way up to like 39 milliliters. So you get the point. I can have many, many, many different answers here, okay? Same thing with this one. As long as it's greater than 40, 41, for example, 42, 50 if I wanted to, they all can be used to calculate the pH after equivalence point. Does this make sense so far? Okay. So with that said, things that I want you to find, okay? Initial pH for when we add 0 milliliters in of my NaOH, the pH after we've added 20 milliliters, the pH at equivalence point, and then the pH at 50 milliliters. So I'll give you a second to copy this down, and we're going to go through this together, okay? We'll do the easy one first, and then we'll move on to the harder ones afterwards. Okay, so for our very first one, let's go ahead and do the calculation. I am looking only at this. I have no NaOH present, so I don't need to worry about that. If I'm looking for the pH, do I really need to care about the volume here? Does that matter as much? No, right? And since this is a strong acid, we assume that this concentration of my HCl should equal this concentration of my H+. Okay, so this is how much H+ I have. Tell me what pH that is. Remember, pH is negative log, okay? So you should get a pH of 1. Any questions about that? Okay, now we'll put that to the side. Let's go ahead and talk about when we've added 20 milliliters of NaOH. So if I write this down, I have 40 milliliters of HCl, right? And it's at 0.1 molar concentration. Here I have 20 milliliters of my NaOH, and it's also at 0.1 molar concentration. Anytime that I am adding acids and bases together, what form do I want them in? Do I want them in molarity? Do I want them in volume? What do I want to solve this in? Or what do I want to add them in? Think back to stoichiometry. Can I just add the volumes together and call it a day? I cannot, right? So I need moles. Okay. You spend a lot of time learning about moles. We need to change everything into moles. This needs to be converted into liters, and then I multiply the two and I get my moles. And once I have my moles, then I can go ahead and add the two values together. All right, I will go ahead and just show you what we have on screen here, so it's a little bit easier. First one, initial, we did that already, so we don't have to worry about that. The second one, we go ahead and change everything into moles. So I should have 4.0 times 10 to the negative 3 moles of H3O plus. Because I have 20 milliliters of this, written as 0.02 liters, it becomes 2 moles, or 2.0 times 10 to the negative 3 moles of OH minus. Any questions about getting to this part right here? No questions? Okay. Now I can interact the two of these together. Remember, I always have more acid than base in my before equivalent step. So this is the amount of acid that I had. I added in some base, okay? So two of these are going to interact, and I'm going to go ahead and make water out of it. So I should have no more base left, and I should use up some of that acid. What I have left over is some small remaining amount of acid. Does this make sense so far? Okay, with that said, we should have 2.0 times 10 to the negative 3 moles of H3O plus left over. I have no more of my base. I have less of my acid now, okay? So with that said, I must go ahead and put these back into my molarity equation. So remember, it is moles over liters. And your liters in this case is going to be the two of them added together, the two volumes added together. For the purpose of this class, we're going to go with the assumption that the two of these are additive and you don't have to worry about any interactions where there is going to be reduced amounts of volume. So we'll assume that 40 milliliters added to 20 milliliters will give me 60 milliliters. This is under the assumption, okay? So with that said, I get the concentration of my H3O plus. At that point, I plug it back in and I get my pH. Any questions about this so far? Okay, with that said, remember, you have added in some base. This pH should go up. So it has gone up from 1, so there is an increase, okay? If I wanted to do this entire equation right here with another before equivalence point, let's say I change this to 0.03. In other words, 30 milliliters, okay? Then this number right here would just simply become 3. This would become 3. This will just be equal to 1. At this point, I change that to 1. This number decreases a little bit. And then finally, this pH should increase a little bit. Okay. Thank you for letting me know. All right. Any questions about changing the numbers? All right. Remember, for B here, you can have multiple calculations, different amounts. Okay. It's not always going to come out to pH is equal to 1.48. But for your A and for your C, those are always going to be set amounts as long as your concentrations remain the same. Okay, so for equivalence point, pH is always going to be 7 if I'm looking at a strong acid, strong base titration. No question about that. It's always going to come out to that same number. Now let's look at the last scenario. In this scenario here, I mentioned that I have 50 milliliters of my NaOH now. So if I look at this, this is how much NaOH in terms of moles that I have. The amount that I have for my acid has not changed. So it's still 4.0 times 10 to the negative 3 moles of H3O plus. So this number has not changed, okay? The only difference is now I have more OH than acid. So when I have more OH than acid, I assume that all of this A is going to be used up, some of this B is going to be used up. What I have left over is just some B. Anyone have any questions up to this step right here? Okay, with that said, now the subtraction is, this is from my acid and this is from my base. I should have some base left over. They usually refer to it as excess base. So to find the concentration, I take that mole that I have here, I divide it by the total volume again. So it's just moles over liters, and I get this concentration. Once I found this concentration, I can actually find the POH or I can find the H plus. But we are not done. You need to make sure you subtract from 14 to get your pH. Anyone have any questions up to this step here? Okay. So with that said, we have reached a place where our pH is going to be a very high number because we have passed the equivalence point. So we've used up all of the acid that is there, but we've added in more base. So that base is essentially just starting to react with the water and whatever else is there. That pH is going to skyrocket up. Okay, any questions before we continue? All right. So the other example we're going to look at, we're going to try to get started with this. Hopefully we can finish it. This is a little bit more complicated. Okay. This time I am looking at a weak acid plus a strong base. Okay. And because not all of this dissociates, we need to account for other things such as the conjugate base. So that is something we're going to have to account for as well. Now, one thing I do want to point out, when we hit equivalence point, the only thing I can say about a weak acid, strong base titration confidently is that when we hit the equivalence point, this pH should be greater than 7. Once again, weak acid, strong base titration, the pH should be greater than 7. Now, is it always going to be 8.8? It is not, but it is definitely going to be greater than 7. Okay. So we'll set up the same way where I have my 4 parts, my initial, my before equivalence, my after, my equivalence, and then my after equivalence. I'll give you a little bit to copy this down, and then we will talk about it. Okay, does anyone else still need more time to copy this before I show them the next 2? Okay, so I'll show you the next 2, let you copy it, then we will talk about all 4 at once and do a practice problem. So go ahead and copy this one down. This is the pH at equivalence point. It is no longer 7. It's obviously going to be more complicated, and we will talk about that in a bit. And then we have the pH after equivalence point. Okay, does anyone else still need more time to copy this down? All right. So let's go back to the first set. I want you to look here. What essentially are we looking for in this area? What does this look like? What does this equation look like? Or if you're unsure of that, what can you tell me about weak acids versus strong acids? Okay, let me rephrase the question then. If I have a weak acid, does it dissociate fully or a little bit?
Little bit.
A little bit, right? So only some H plus is going to come out of that weak acid. Such a small amount that we need to figure out how much that is. And we need to use our ICE table to figure that out, right? And when using my ICE table, I can actually simplify my ICE table by writing this. The concentration of my H3O plus is just simply equal to the square root of my Ka times my initial concentration. So after going through the ICE table, you should end up with that. And you should be able to plug this in and solve for that. So this is my weak acid equilibrium equation. Because right now, all I have is just my acid, but it is not a strong acid, so only some of it dissociates. And I need to find out what that pH is for that small dissociation. Now, if I look down here, what is an equation that you notice is showing up? What equation do you notice down here that you learned about today? The Henderson-Hasselbalch equation. And if you see this, what is that telling you? We are dealing with what? Buffers, okay?
Conjugate.
It is to deal with the conjugate, but we're dealing with buffers. So if I go back to here, if you look carefully, this is known as the buffer region. So remember, this is your initial, this is your equivalent. The stuff in between, the before equivalent, there is a buffer region. And we're going to talk about that in a bit, okay? So for this one, at equivalence point, if you notice, this is no longer just 7 because we need to account for what is present there. And we'll talk about that in a second. And the last one here, oh, sorry, here you go. Last one here is very, very similar to the after equivalence point of a strong acid, strong base titration. Because all we care about mostly is the excess OH and how that affects my pH. So this one is almost the exact same. You don't have to worry as much if you learned one of them. Okay. Let's look at a scenario here. We're going to try to do this scenario together. They give you, again, 3 different parts here. Okay. Good news is, again, concentration of my weak acid and my conjugate and my strong base are equal to each other. You notice I didn't say conjugate base, just my strong base. Okay. These are equal to each other. So then I only have to look at the volume. Okay. We know that 40 milliliters here, because it's matches to 40 milliliters in concentration, this is my equivalence point. This is my after equivalence point, and this is my before. And then this is my initial. Any questions? Okay. With that said, do you need a minute to copy down the question? Or can we jump right into it? All right, give me a few seconds with it. Okay, so let's take a look at our initial. Very straightforward. I can do the ICE table, go to the whole format, or I can simplify it here. Remember, this is only of my weak acid. There is no base at all. So I'm not involved with any kind of base here. It's only my weak acid. This is my simplified way of solving for the X, which is my H3O plus, which then I can do the negative log and find the final answer. Okay. Any questions on my weak acid equilibrium, solving for the pH of that? Anyone unsure of what to do there? Okay. The next part. I'm going to write this as weak acid so you can see what I have here. And I am adding in some kind of strong base. Okay. So this is for our B. the next one over. Now, with this said, which one is in a greater concentration, weak acid or strong base at before equivalence point? Which one do I have more of? Or which one should I have more of? I should have more of my weak acid, right? So I'm gonna write that a little bit larger so you can see. There should be more weak acid, some strong base that I've added in, okay? With that said, if I use up all of the strong base, no, to clarify, not for A, for the equivalence point, which is C, pH would be greater than 7. For any acid in general, if I'm looking at the weak acid equilibria, then it should be a pH less than 7 because it's just the weak acid, okay? So I use up all the strong base, I use up some of my weak acid, okay? What I have left over is a little bit more of my weak acid here. But now, normally, if I was dealing with a strong acid, strong base, they fully dissociate, they will not rejoin together, we don't care. What do I know about weak acids? If I use up some of that weak acid, what do I have left over? The conjugate base, okay? Now, we have to write down the conjugate base because it actually makes a difference here. This conjugate base is stronger than water, so it will have an effect. So we need to account for this in my equation. Now, once I'm done doing this, right, this is my initial, I end up with some of my weak acid, some of my conjugate base. My strong base is all gone. Some of my weak acid is gone. What do you notice about this? What is this and this? I have some amount of weak acid, some amount of my conjugate base. What is this? Yes, I know that is a weak acid. What are the two of these combined? Remember, this is the conjugate base of that weak acid. It is a buffer. Okay? You have some weak acid plus conjugate base. You have essentially made a buffer in this scenario. Okay? So that is why if we go back to the very beginning, you notice that the line kind of stays flat before it goes up. This is because the pH barely changes. Okay, so let's take a look at how we can calculate that buffer information. So we treat this the same exact way we were doing before. This is my initial amount of HPR. This is my acid, okay, my weak acid. This is the amount of my strong base, okay? With that said, when I add them together, all of my strong base is going to be used up. So this is all gone. So I fully use it all the way up. This is gone. I take away some of my weak acid. I should only have this much weak acid left over. Does this make sense to everyone so far? Take your silence as a yes. If I take away this H right here, the hydrogen from this weak acid, what is this? What did I make? If I take away the hydrogen from the acid, what did I make? The conjugate base, right? This is that. So that is why I'm adding this in. So I have some amount of my weak acid and conjugate base here. So this is what I have in my solution. Okay. Now, we set this up in terms of my equilibrium expression. I plug it in. This is what I get. If I wanted to use the Henderson-Hasselbalch equation, I can do that as well. This gets changed into pKa. This gets counted as my concentration. And then here I have the pH. Okay. Any questions on this up to this part here? Okay. Does anyone need time to copy it down? All right. So with that said, I can go ahead and plug this in, solve for my pH. If I wanted to use my Henderson-Hasselbalch equation, I can plug in these numbers here. Now remember, these are usually in moles, okay? You want to change this into molarity, but the good news is if this is moles and this is moles, right? They're both going to be divided by some liters, so the numbers are essentially the same ratio, so I don't need to do that. I can save myself an extra step. The ratio here is going to remain the same for molarity or moles. It will be the same exact thing. Okay, any questions up to this step here?
Professor, yeah, I just wanted to, so let's say the problem asks us for all the information given, but it also takes into account the H2O. Since it already has the pH of 7, then it would just be changing down to being more basic then in this case, correct?
If we're going to talk about H2O, it is liquid. It is not included in our equilibrium expression. We don't ever include it. The only time we include it is if it is interacting with something that is changing and making more H or OH minus. In this case, it is not doing either. So I don't care about the water. This liquid, I can ignore it.
Oh, no, but I'm saying if it did interact with it, let's say that there's 3 concentrations in the reactants, and they somehow all got to 1, we would still take into account it, right?
So we'll talk about water when we talk about just the conjugate base reacting with the water. So in other words, when we get to C, the equivalence point. For the purpose of this, we're focusing on just the weak acid and conjugate base. Okay.
Okay.
We don't have any of my strong base left. It's all used up. I don't care about the water in this case. Okay.
Yep, thank you.
All right. Does anyone else still need to copy this before I move forward? All right. So in the next scenario, before I show you any of this stuff, I have weak acid, okay? And I have strong base. I have an equal amount for the 2 of these. What can I say happens once I am done interacting with these 2? Do I have any weak acid left?
No, they should cancel.
Should cancel, this should cancel, right? But this doesn't mean that we have nothing left, because the weak acid, when I go ahead and use up the weak acid, what is left over from that weak acid?
Isn't it CB?
Conjugate base, okay? So this amount that we have for the strong base, this amount we have for the weak acid, all of it's used up. I have that amount of conjugate base. The conjugate base of a weak acid, I want you to talk about this in terms of strength, okay? Base strength. The conjugate base of a weak acid, is that stronger or weaker than water? It is stronger, okay? If I spoke about the conjugate base of a strong acid, then in terms of this conjugate base, it should be weaker than water, okay? When it's weaker than water, it will not interact with water at all. It will not try to pull off an H or give an H away. This will have no reaction whatsoever, and we don't care about it. But because this is stronger, what do bases tend to do?
It should get more basic.
What does a base do?
It decreases the amount of acidity, so basically lowers the pH down to from wherever it was.
It actually
Let's say
raises the
7 down to
pH.
6.
But I want you to clarify this though. What does an acid do? We're going to look at this in terms of the Bronsted-Lyer definition. What is the definition of an acid? It donates what? H plus. So then what does a base do?
It removes H plus.
It removes or accepts H plus, right? So it wants H plus. In order to get H plus, where is it going to get that H plus from? Where's the only source of H you can get H from?
The water.
Water. So it takes in that H. When I take away an H from H2O, what do I have left over? OH minus, okay? OH minus is going to cause my solution to be slightly basic. So that is why in this scenario, since I only have the conjugate base and it's going to interact with my water, this is going to have a pH that is greater than 7 because it is causing some OH minus to be formed in my solution by taking away the H to join with that conjugate base. Does that make sense? This goes back to our salts, kind of. A little bit talking to our salts, okay? So with that said, let's plug everything in. 0.004, all of the values, all of my OH and all of my HA is used up. So all I have left is just my A minus, which in this case is just my conjugate base. Okay. Conjugate base, I must change this into concentration wise. So I do the same thing here. The moles over the total volume gives me this concentration here. Once I'm here, okay, I can just plug in the information I changed that into KB instead of KA. Remember, this works because it is a conjugate. With the conjugate base and a weak acid, right? Or a conjugate base of an acid, the Kas and Kbs are related by Kw. So Ka times Kb gives me Kw, only for conjugate acid-base pairs. So with that said, this is my Kb, this is my concentration. Don't worry so much about the setup for this part here, but generally speaking, with these two things, I can find the weak base equilibria. So I can use that to find OH minus. They did this extra step right here to simply get right to H plus to save us the trouble. Okay. And then at that point, use the negative log. This number is greater than 8. Any questions about this one so far? Okay. Does anyone need time to copy it, or can I move forward? Any time to copy it? But just to clarify, if you need time to copy it, type yes. All right. I'll give you a little bit of time to copy it. Then we're going to finish with the last one, which is part D, and then we'll open up the polls. Okay, so let's go ahead and move on to our last part. So in this scenario, remember, we have 50 milliliters. That means we have more strong base than we do of our weak acid, okay? Plug everything in. All of my weak acid is used up, so all of that is gone. I have some excess OH minus. That comes out to about this much, okay? I set up the same way. My excess OH minus over my total volume. I get this concentration right here. And I plug it in. I find my pH as 12.05. Now, some of you are probably wondering, what about that conjugate base that we have? Okay, we had some concentration of it. We had about 0.004 moles of conjugate base. This must contribute some amount, right? Because this is already going to make our solution basic. So why don't we account for this? And when we look at this, I'm going to go back real quick. Okay, I want you to write down this number right here. This is the concentration of my OH minus. Okay, so give you a second to write that down. And then we're going to go back to our previous slide to see how much OH minus we kind of can make given the information that we have. Okay. So going back to C, I want you to take this number and do KW divided by this number. That will give you my OH, give you your OH minus. So this is based on what it is. It's probably 10 to the negative 5, give or take. Okay. In a little bit. So this is going to come out to about 10 to the negative 5 in terms of my OH concentration. I want you to compare it to this number. If I had to write this in a scientific notation, what would this be? 10 to the negative what? Ten to the negative 2, right? Compare 10 to the negative 2 to 10 to the negative 5. How much more larger is this compared to that? A 1,000 times, right? So whatever amount of OH that you might get from the conjugate base is 1,000 times smaller than the OH that you get just from your strong base. So this is so insignificant that I can just ignore it. That is why our equation here focuses only solely on the OH that comes from the strong base. Okay. And so that's why we can get a pH of this. If I tried adding in that thing, it would probably be a difference of like 0.0001, like this little difference right here. That was what it would be here. Okay. That would be the only factor that would may be affected. Again, it's so minor that I don't really care about it. Does that make sense so far? In case you were wondering what happened to the conjugate base. Okay, does anyone else still need more time to copy this down? All right. So we're gonna stop here for our slides and we'll continue next time. I will go ahead and send out the polls now. Before I do that, for the two co-hosts that are currently recording, I want you to go ahead and stop the recording. So this way you don't lose it when I remove co-hosts privileges, okay? Okay, I'm gonna open up the polls real quick. There are 4 questions. You can go ahead and begin those. I give you about, based on what time it is, 3 minutes to answer those questions. Okay, you have about 1 more minute to answer the questions. I will stop it at the 3-minute mark, so about 60 more seconds left. Okay, you have about 30 more seconds. Also to let you know, during office hours today, I will go over chapters 16, 24, and 17 for the quiz. So if you have questions, you can ask me then. Okay, you have about 10 more seconds. So if you haven't answered it, go ahead and answer the questions. Once again, you have about 10 more seconds. All right. I'll try to see if the recording works. Okay, I'm closing the poll now. So looking through this really quickly, number 1, it should be resist the change in pH for both acids and bases. I see almost everyone got that correct. Second one, how does a buffer work? It is the common ion effect, not the neutralization effect. That is not something that we've learned about, okay? It is the common ion effect. Most of you got that one wrong. Third one, which of the following are considered buffers? There's only 2 combinations, weak acid plus its conjugate base, and a weak base plus its conjugate acid. And the last one, when do we use the Henderson-Hasselbalch equation? Anytime you have a buffer, not because we're mixing acids and bases. So those could be strong acid, strong base mixtures. It won't make a difference. Only when we have a buffer. Okay, so with that said, during office hours in about 5 minutes, 10 minutes max, I will start that. We will go over the 2 quizzes and any questions you might have. Other than that, we are done for today. I will see you all next week. You too, enjoy your day. I will try to record office hours. Again, it's always hit or miss whether the recording works or not, because I'm going to be in the middle of transferring this recording. So if this is the middle of transferring this recording, it will not save the next recording. So that's usually the case. I will let you know, again, it's hit or miss. Okay. If I'm recording, if it's downloading this recording, it will not load the other recording or try to save the other recording. Yes, next week you have a quiz on chapter 18, and the week after that, you have chapter 19. All right. Any other last minute questions before I close out the session? Same login for office hours. Yes. Okay. So I'll see you all during office hours or next week.